There. Okay, so this week's agenda is as follows. So number one is to compare two different perspectives on the dihedral group. And namely, one is what they'll call the old perspective, and the other is using matrices. So that should have been what you've learned. I mean, that is what you've learned this week, according to your professor, about orthogonal matrices, like symmetries of the plane. And the second item is to prove that the orthogonal group is actually a group. The orthogonal group is usually called O of n. So let's do it. Yeah, so first the dihedral group. Before I start, I should review just briefly review how symmetries can be expressed as matrices. So recall that for a reflection, so rotation of theta counterclockwise, that's represented by the matrix, is represented by this matrix, cos theta, sine theta, negative sine theta, cos theta. And then a reflection about a line L making an angle of theta with the positive x-axis. So that can be depicted by this picture. So this is the line L, this is the angle theta. This can be represented by this matrix. Cos 2 theta, sine 2 theta, sine 2 theta, and negative cos 2 theta. So note these matrices are extremely similar, right? They're really the same. First of all, there's a factor of 2, and the signs are different in the second column. But otherwise, the form is very similar. And one thing to note, there are two choices for theta for any reflection. And they differ by pi. And I'll draw a picture to show you what I mean. So if I have this line L, I could choose this to be my angle theta, but I can also choose, whoops. I can also choose this to be my angle theta. And this is theta plus, this is the original theta plus pi. So those are both equally valid angles. And they give the same matrices, because when you multiply by 2, you get 2 pi. So changing by pi won't change any of these cosines and sines. Changing theta by pi. Right. So those are our matrices. And now let's actually get on to the dihedral group. So the first example that your professor suggested was to compute D times H in D4, right? Yes. So we'll just write down the matrices for both. So for D, so this is a reflection, and this angle is 3 pi over 4. Matrix for D is cos, I just used the formula for before, so I'll get cos 3 pi over 2, since I multiply by 2, sine 3 pi over 2, sine 3 pi over 2, and negative cos 3 pi over 2. And if you actually compute what these numbers are, you get 0, 0, -1, 1. And you could have found this directly by just thinking about, like the map is simple enough that you can compute this matrix directly without even using the formula, but in general, it's easiest to just stick to one method. Just always use the formula, because for, like you'll see, we have another example in D5, you can't compute it as easily directly. So, and now for H, again, the matrix can be computed directly. What I mean by directly is you don't even need to think about cosines and sines to actually find the matrix, but I'll just stick to the general method. So this angle is pi. So the matrix for H is cos 2 pi, sine 2 pi, sine 2 pi, negative cos 2 pi. And if you plug everything in, you'll get 1, 0, 0, -1. Okay. So then the matrix, so remember from, hopefully you've learned this in your linear algebra course, but matrix multiplication represents composition of maps. So if you have like two different maps, also, I'm not sure if they use the word map in this course, but map and function, they're interchangeable words. Like just reflecting is a map, rotating is a map. But yeah, if you have a bunch of functions or maps and you want to compose them, well, to get the matrix for that, you just multiply the matrices of the maps. That's the whole point of matrix multiplication. So in this case, the matrix for D times H is the product of these two matrices. So it's 0, 1, -1, 0 times 1, 0, 0, -1, which is 0, -1, -1, 0. Hopefully I did that right. Yeah, I think it's right. Does anyone see immediately what symmetry this corresponds to? Okay, if not, then you can just solve to find the symmetry. Just solve 0, -1, -1, 0 equals cos theta sine theta plus minus sine theta minus plus cos theta. So I'm putting these plus minuses and minus plus to represent that, you know, I guess I shouldn't know whether, if I didn't know whether it was a rotation or reflection, then I have to take into account that either the top can be plus and the bottom minus, and that's if it's a reflection, or the top minus and the bottom plus if it's a rotation. But actually, I know already it's going to be a rotation because the product of two reflections is a rotation. But anyways, if you solve, you get theta equals 2 pi, and the matrix is cos theta, sine theta, sine theta, negative cos theta. Something seems wrong. Does anyone see any mistakes I made? Doesn't seem right to me. Yeah, the product of two reflections is a rotation. Okay, my matrix for D is wrong. Somewhere I went wrong for my matrix for D. Right, because I did the, what did I, oh yeah, so for some reason I didn't put this as -1. So that's actually the matrix for D. So this is -1. So that means this is 1. So this is also 1. And this makes more sense. So that's why it's good actually to know that things like the product of two reflections, rotation, stuff like that. So if you mess up, you'll know when you messed up and you can go back and fix it. But yeah, this is what I would have got if I did my calculation correctly. So the matrix is this. So it's a reflection. Summarizing, 0, 1, -1, 0 is equal to cos 2 pi. Was it 0, 1, -1, 0? Yeah, 0, 1, -1, 0 is cos 2 pi. Oh my God, I made another mistake. What am I doing? So it's 0. So theta, wow, I am totally off my game. Theta should be pi over 2 or 3 pi over 2 to get 0. And since sine theta is -1, it's 3 pi over 2. Sine theta equals -1. And so that means cos theta (0, 1, -1, 0) is cos 3 pi over 2 sine 3 pi over 2 negative sine 3 pi over 2 cos 3 pi over 2, which is the matrix for rotating 3 pi over 2. So if you go back and look at the description for rotations and reflections, this exactly matches the matrix for R3 pi over 2. So D times H is R3 pi over 2. And we can verify this directly using the old way. So right now we used matrices. Using the old way, the way at the beginning of the course, and this way isn't supposed to be easier for the record, it's just supposed to give you a different perspective. Obviously, if you're actually supposed to compute something in the dihedral group, it's much easier to just use the old way with pictures. This is more just, I don't know, a different perspective. So let's label 1, 2, 3, 4. Then we apply D. We apply H. So we get 1, 4, 2, 3. Then we apply D. So we get 3, 1, 2, 3, 1, 4. And on the bottom, if I just do R3 pi over 2, I'll get the same thing. So this is another check that our calculation was right. Now, the second example that your professor suggested was to compute R 2 pi over 5. Second example your professor suggested was to do a calculation in T5. I was going to write what the calculation was, but I figured it's better to actually tell you my notation for D5 first, and then I'll say what the calculation is going to be. T5, first, we'll list the elements of D5. So there are the rotations. And you can rotate by, so these are the elements. So there's R theta for theta equals 0, 2 pi over 5, 4 pi over 5, 6 pi over 5, 8 pi over 5. And you saw before that the matrix, when you could just plug in theta to this matrix, and you get the matrix for R theta. There are also the reflections, and this is really where I actually need to specify my notation. So I'll label my vertices of D5 first. So this is how I'll label them. And remember that it's a regular pentagon, so all these angles should divide the central angle of 2 pi into 5 equal pieces. So these should all be 2 pi over 5. Okay, so what are my reflections? So I'll just label the lines, the possible lines, according to the vertex they pass through. So there's one reflection. I'll call this reflection, I'll call this line L1 because it's the vertex through vertex 1. I'll call this line L2. I'll call this line L3. Call this line L4. And I'll call this line L5. So now I have to find the angle each of these lines makes with the positive x-axis. So because of the description I gave for reflection matrix, I need to know the angle that each line makes with the positive x-axis to find the matrix. So what is the angle for L1? So what is theta? Does anyone know the answer? It's not. So to find theta, you take this bigger angle in pink. So the pink angle is pi over 2. And then the angle between any two vertices is 2 pi over 5. So theta equals pi over 2 minus 2 pi over 5, which is pi over 10. And then the remaining angles are easy. So just add multiples of 2 pi over 5. So for example, I'll just do L2. Actually, yeah, I'll do L2. So for L2, so for example, for L2, add 2 pi over 5 to the angle for L1. For L3, add 2 pi over 5 to the angle for L2, and so on. So I'll record this information in the table. So there's the line and the angle with the positive x-axis. And the reason I'm doing this, recall, is I want to do a computation in D5. So I have to know how each element of D5 is represented as a matrix. So for the reflections, I have to know the angle that each reflection makes with the x-axis. Of course, I could have oriented my pentagon in a different way. So keep in mind that the angles depend on how you orient the pentagon, although the final answer won't change. I chose to do it in a way that isn't too hard, but also isn't too easy. So I wanted to do a little work in finding the angle for L1. If I picked vertex 1 to just lie on the x-axis, that would have been the easiest. So it just would have been, the angles would have been 0, 2 pi over 5, 4 pi over 5, etc. So they're slightly shifted now, and that was intentional. So for L1, we already find the angle, it's pi over 10. And recall that you can also add pi and you'll get a valid angle. So here, this discussion on the bottom, there's two choices of an angle for every line. For L2, we add 2 pi over 5. So it's pi over 2 or 3 pi over 2. For L3, again, add 2 pi over 5. So it's 9 pi over 10 or 19 pi over 10. For L4, it's 13 pi over 10 or 3 pi over 10. And finally, for L5, it's 17 pi over 10 or 7 pi over 10. So those are our angles. And given an angle, we know how to find the matrix. Now I'll actually tell you what the computation is. So we're supposed to compute r 2 pi over 5 times f of L1. So r 2 pi over 5 is represented by cos 2 pi over 5, sine 2 pi over 5, negative sine 2 pi over 5, and cos 2 pi over 5. And for f of L1, the angle L1 makes with the positive x-axis is pi over 10. So f of L1 is represented by cosine pi over 5. Remember, I have to multiply by 2, the angle. Sine pi over 5, sine pi over 5, cosine pi over 5, negative. And then the product is just represented by the product of these matrices. So r 2 pi over 5 times f of L1 is represented by cosine 2 pi over 5, sine 2 pi over 5, negative sine 2 pi over 5, cosine 2 pi over 5, times the matrix for the reflection. So now I just multiply it out. So I'll get cosine 2 pi over 5 times cosine pi over 5 minus sine 2 pi over 5 sine pi over 5. That was all just for the first entry. Second entry will be this. This is the third entry. And the last entry is this. Whoops. Oh my God, I did it wrong again. There. And these should look familiar. I mean, if you're familiar with the trig addition formulas, then you can recognize that these expressions all fit the patterns. So using trig addition formulas, this will be cosine 3 pi over 5, sine 3 pi over 5, sine 3 pi over 5, negative cosine 3 pi over 5. And this fits the pattern for a reflection matrix. So this is the reflection. So this is a matrix for reflecting dotted line making an angle of 3 pi over 10. So remember, you have to divide by 2. So if you have the angle, you multiply by 2 to get the matrix. If you have the angle in the matrix, you divide by 2 to get the angle for the line. Positive x-axis. So now I have to go back to our table. And where does 3 pi over 10 show up? There. So it showed up there. And so that means that this is a reflection. So it showed up in the entry for L4, about L4. So we get our 2 pi over 5 times f of L1 equals f of L4. Now, let's check using the old way. The old way is easier, for sure. So first we do f of L1. This is L1. Then I do R 2 pi over 5. So everything shifts. And hopefully this is all the same as just doing f of L4. Yes, it is. So our calculation was correct. Okay, and now we just check that ON is a group. So that's the second order of business. Prove that ON is a group. ON is the set of matrices with real entries, n by n matrices with real entries, such that A transpose equals A inverse. If you prefer more like, I don't know, verbal definition, kind of qualitative definition, I don't know how to say it, but it's a different way of thinking about it, is that equivalently orthogonal matrices are matrices whose columns form an orthonormal basis. But for proving that ON is a group, this is not that useful, the description on the right. So to check it's a group, we have to check that it's closed under the group operation. So suppose A is an element, A and B are elements of ON. So A transpose equals A inverse, and B transpose equals B inverse. That's what it means to be an element of ON. Now, applying the group operation gives AB. So we have to check that AB is an element of ON. So does it satisfy the condition for being an ON? Well, AB transpose is equal to B transpose A transpose. This is a general property of taking transposes. This has nothing to do with ON. It's just a property of matrices. I mean, all that transposing does is switch rows and columns. So somehow you multiply then transpose. You could have just transposed at the start and multiplied, but you should reverse your matrices. But this has nothing to do with ON. But for the next line, I could change B transpose A transpose to B inverse A inverse. And this is because B transpose equals B inverse and A transpose equals A inverse, since A and B are in ON. And for the last line, B inverse A inverse is the same thing as AB inverse. This is again, this last line is just, this last equality, I mean, is a general property of inverses. So for any matrices, AB inverse is the same thing as B inverse A inverse. And in general, in any group, that's the case, because just logically, I mean, if you apply B to something and then apply A to something, well, to reverse that, you reverse A first, and then you reverse B. So if you take 2 steps, you just reverse those 2 steps. So this always works in any group, that AB inverse is B inverse A inverse. So AB, we've shown that AB transpose equals AB inverse. Hence, AB is an element of ON. So we've checked that ON is closed under the group operation. Next, we have to check that it contains an identity element. The obvious choice, well, I don't like the word obvious. I'll use the natural choice for the identity is to take the identity matrix I use identity matrix in quotations to avoid any confusion, because the name of the matrix is the identity matrix, but that doesn't mean it's necessarily the identity for ON. It is, but just because it's named that doesn't mean it is. It's named that because it's the identity for all matrices, but we have to check that it's actually in ON. So the identity matrix has ones on its diagonal. The identity matrix, so IN satisfies IN times A equals A times IN equals A for all matrices. So all we have to check we just have to check that IN is an ON. So it already satisfies the condition we need for it to be an identity for ON, because it's an identity for all matrices. So applying it to any matrix gives you back the matrix. So it definitely works in ON too, but we just have to check that it's actually in ON. So is it an ON? Well, IN inverse is equal to 1, 1, 1, 0 inverse, which is just the same thing again. And this is also equal to its transpose. So we have a check mark. It is an element of ON. And actually, if you understand the philosophy behind ON, you could see that IN would be an element of ON before you even do this calculation, because the whole point of ON is it's linear maps which preserve distance. So the identity matrix, or linear maps, if you like, it's matrices that preserve distance when you multiply them by a vector. Well, the identity matrix just preserves every vector. It just doesn't change any vector. So of course it preserves distance. Right, so the identity is an element of ON. We have to check that multiplication is associative. And this follows immediately from the fact that matrix multiplication is associative for all matrices. I mean, i.e., A times B times C equals A times B times C for all matrices A, B, and C. So in particular, it holds in ON. The last thing we need to check is that it's closed under inverses. So let A be an element of ON so that A inverse equals A transpose. Then we have to check, we must check that, well, first, note that A inverse times A equals A times A inverse equals IN. And this is the identity for ON. So A inverse, it's a bit confusing because the inverse, you have to keep in mind what group you're speaking relative to. So A inverse is referring to the inverse of A just as a matrix in general. So it's before you even knew about groups, you know what A inverse means. And now we're talking about what's the inverse of A in ON, but it turns out because ON is a group under matrix multiplication, I mean, the inverse of A in general should also work here, because I mean, the identity for ON is just your normal identity, and A inverse satisfies the condition that A inverse times A equals A times A inverse equals the identity. So it is the only candidate for an inverse. It is the only element that could potentially be the inverse of A in ON, but we have to check that it's actually in ON. So we just need to check that A inverse is an element of ON. So A inverse transpose is equal to A transpose inverse. This is a general property. It's a general property that holds for all this holds for any invertible matrix. And for the next line, I'll actually use the fact that A is an ON. So this is equal to A inverse inverse. That's because A transpose equals A inverse, since A is an ON. So A inverse transpose equals A inverse inverse, which means A inverse is an element of ON, which is what we want to show. So O of N is a group. We've checked everything. And that covers everything for today. So I'll end the recording. So I end the recording. Where's the button?